Good morning all together. My name is Peter SCHOSSIG and I'm leading the division of thermal systems here at the Fraunhofer Institute of Solar Energy Systems. And our main work for heating systems, meanwhile, is heat pumps. We're looking at all kinds of thermal systems, from solar thermal to heat pumps to even high temperature solar heat for concentrated solar power. But we have a major division which is working on heat pumps. And today I have the pleasure to give you an impression of one specific technology inside the heat pump family, and that's fuel-driven sorption heat pumps. I was already introduced to AIE work, and one of the working groups inside the AIE heat pump program was this Annex 43, which was dedicated to these fuel-driven sorption heat pumps. And I had the pleasure to lead this together with some colleagues for the last 4 years. And I will give you a short impression about the work we did and what these kind of heat pumps are mainly useful for. So maybe first an introduction, what are fuel-driven sorption heat pumps? On the right side, you see a schematic drawing of any kind of heat pump. You have any kind of driving energy, which is pumping up heat from a low temperature heat source to a useful temperature level of heat. And normally you use mechanical energy or electricity to drive this process, but there are several options where you can use heat as the driving force to drive this thermodynamic process. So basically then the two temperature flows, or the heat flows from the high temperature level and the low temperature level, add up to be delivered as the useful heat in the medium temperature level, which is needed for the heating system and domestic hot water. On the left side, you can see an example how this is working. I will give you only a short introduction, and the link below, you have a very detailed animation which gives you a further explanation. But basically, you burn a fuel, for example, gas, to separate two substances. Here is an example of a water ammonia heat pump, and then you use the heat to separate the ammonia, which is then driven out of the water to the gaseous phase, which is then going as a gas to the condenser, where it's condensed like any conventional refrigerant and delivering heat to the heating system. After the condensation, you have an expansion valve and you go to the evaporator. With ammonia, you have here now temperatures far below zero, where you collect the heat from the environment and then go to the absorber, where you recombine now the ammonia, which is now cooled down again, but heated up from the environment. You combine it again with the water and come back to the water ammonia solution. And here you have a small solution pump, which pumps the solution between the generator and the absorber. So basically this part here, where you have these two solutions, is something like a thermal compressor. You use the same process of compressing refrigerant, here it's ammonia, but you don't use mechanical energy to compress this, you use heat and use this in a kind of sorption process where you separate water and ammonia. So this is the basic technology behind using heat to separate substances and drive an evaporation process and a vapor compression process behind. But the difference is you use fossil fuel or any kind of heat source instead of electric energy. So this will lead to different definitions of performance figures. So you have the CUP in a very similar definition like in a compression heat pump, but here you have the energy delivered in terms of heat, which you need as a driving force, divided by the useful heat you bring to the building. That means usually, while you have a CUP for a compression heat pump in the range of 3, so out of 1 electricity kilowatt hour, you generate maybe 3 or 4 of heat. Here it's different. Normally the heat CUP of a heat-driven heat pump is maybe 1.5. So you generate out of 1 kilowatt hour of heat, 1.5 kilowatt hours of useful heat for the heating system, because you pump in 0.5 kilowatt hours from ambient heat. But this is not fair to compare 1.5 to 3, because the primary energy content of the heat delivered is different than to electricity. So it's a lot of systems where it might be useful to save primary energy anyway by this kind of a heat pump, and it's not useful to compare the CUP directly because it's a different form of energy going into the system. Therefore, it's more useful to take the so-called gas utilization efficiency into account. And that's the factor which you have effective heating load compared to the heating input all over the process. And you do this like the seasonal performance factor for a heat pump. Here you have the seasonal gas utilization efficiency SGUE, which is so comparable to the seasonal performance figure of a heat pump. But here you can directly see how much gas you saved compared to a standard normal boiler. So these are the figures of merit. So we're now coming back to the working group of the annex we operated for the last couple of years. It was interesting to see that even in the previous presentation, one of the big market barriers was that the people don't know about this technology. It's simply not known and there's not enough trust. So this is even more true for these small applications of fuel-driven absorption heat pumps compared to compression heat pumps. People don't know about it. So our scope was that we widen the use of fuel-driven absorption heat pumps, especially in residential and light commercial, and basically for the heating mode. And we tried to identify these market barriers, but also the opportunities, how to implement these kind of heat pumps. We made a large study to identify the potential of these applications and to show that there is an importance of this kind of heat pumps in future energy systems. We identified measures to bring these products into the market and to enable a sustainable market entrance and to push development. So these have been the goals, and we hope to reach at least part of them. So the participants have been a wide range of countries. Germany in forms of Fraunhofer and a lot of companies. So basically this annex was a very nice cooperation between academia and several companies. You see that Fraunhofer ISE from academia cooperated with Bosch, Viessmann, Feiland and Stiebel and others. In Italy, we had Politecnico di Milano leading together with the National Research Institution CNR, but also companies. In UK, it was the University of Warwick. In France, it was ENGIE, GRDF, and the company Boost Heat participating in the meetings. In Austria, it was the Austrian Institute of Technology and University of Graz. USA did a very good job, the Oak Ridge National Lab, and together with the company Stone Mountain Technologies. And we had in Korea the Research Institute for Energy Research, and in Sweden also several companies like Saltix and Alfa Laval and the University KTH. And the annex is already over. At the moment, the final report is undergoing the final review and the executive committee, and it should be published in maybe 2 months from now, and you will find it then on the web pages below, as well as several other useful documents you can find to learn out more about this technology on the web pages below. So coming to the main outcomes of this annex. So we have, for most of the participating countries, we have very nice market reports. What is the share of the heating systems in which country, the age of the buildings, the type of the buildings, and for which kind of these buildings, maybe heat pumps and especially absorption heat pumps might be appealing. A very nice outcome is that Oak Ridge generated an absorption database for working pairs, which is now available as an open source software where you can play around to develop new types of heat pumps. We did a lot of development projects together with these companies to develop specific components. You see some nice examples in the pictures on the right side. So we developed new generators and absorbers for absorption heat pumps, as well as other components and systems which are now coming closer to the market. So it was a really nice cooperation between different companies, all together between the companies and research institutions. Based on these developments and measurements, we did a lot of simulation studies to figure out in which countries and climates these heat pumps might be useful. We did some field tests, also less than expected because we have been slower than planned. But we have done some field tests and we developed recommendations for field monitoring projects to really compare apples with apples. We did a lot of dissemination work from conferences to workshops to really make this technology more known and especially accepted by the planners and decision makers. We also did pre-normative work because for these technologies, we also need standards for measuring of performance figures. And of course, AIE is not a normative body, but we did a lot of pre-normative work and filed our knowledge and recommendations to normative bodies. And this is now taken into account in the next round of normative updates. So to highlight the outcomes and the work we did, we had extremely good networking between academia and industry, and also decision makers in policy to bring quicker shortcuts from first ideas generated maybe in academia to concrete development projects. And some of these developments we did are now coming closer to a market entrance development. But we did a very good job in dissemination in terms of workshops. We had some international workshops attached to international conferences, but we did some workshops in the different countries in local language with planners, installers, and decision makers to bring this knowledge to really the people who install this now in the field, that they know there are products and they can trust them. But we also had this international community to stimulate their more research and as well as knowledge. So we made 2 nice conferences, more than 100 participants, just dedicated to sorption heat pumps. Out of these conferences, we generated 1 special issue in a very widely accepted journal, Renewable Energy Reviews, with several interesting papers about sorption heating and cooling, which is now available. Very nice was this pre-normative work where we did the round-robin test among 4 labs, sending around 1 market available heat pump to different labs, and tested along different national and international standards to see if the results are comparable. And we learned a lot of this and improved these standards or made proposals how to improve these standards to the normative bodies. And we have a very nice software now freely available to play around with different sorption pairs for future generation of heat pumps. And basically, it comes down to the point that we had a highly good interaction between academia and industry to bring products to market faster. So now some examples of the results. As said, we did a simulation study. Several simulation studies with different tools in different countries to see in which countries we can expect how much energy savings from cold climates like Potsdam and London to warmer climates like Strasbourg and Milano or Paris. And what you see here is the seasonal gas utilization efficiency. So basically it's a ratio how much gas you saved compared to condensing boiler or conventional system. We looked at multifamily housings with several units and medium heating temperature systems, so slight retrofit or not too old multifamily housing, but replacing an existing heating system. The blue bar is the efficiency for the domestic hot water preparation, and the yellow bar is the efficiency for the heating system. So gray, you see the overall savings for the domestic hot water preparation in this multifamily housing, including heating system. And you see here that the savings are ranging from 32% to maybe 35, 36% all over the different climates for multifamily housing in retrofit. So basically what you can say, including the domestic hot water preparation, you can save between 30 and maximum of 40% of primary energy or basically gas compared to a non-heating system by a heat pumping system by just burning the gas. So basically the message is for installing and retrofitting it in compared to gas, you can save 30% of gas and also then of running costs. That's the message. And we also did field tests, as said. This is just one demonstration project with a commercial available heat pump with the water ammonia heat pump of 40 kilowatt. It's an target was to demonstrate you can do it even in a residential area and still do significant energy and CO2 savings in a real life project. It was a very old school, almost 100 year with a rather high energy demand for heating, but not much domestic hot water preparation. The original heating system was a very old low temperature gas boiler, and the new heating system was a gas driven heat pump, these 40 kilowatt for base load, and a very big peak load boiler. So this was designed for optimal economic decisions. So the heat pump was only for part of the load and not for peak loads, because this is better for the running costs of the system at the end. So and the target was to reduce the overall energy consumption by 30%. Here you see a picture of the building. It's these early 30s, late 20s in the last century, somewhere in Germany. And you see the basement where you have the installation, and here you see the outdoor unit of the heat pump in the backyard of the school, and the large storages in the inside part, and the peak boiler. And now here you see the results for 1 year for the different months. On the left side, you see the efficiency for the net calorific value of the gas, how much we saved for the different months, and you see that we have been able to save maybe 40% for the different months for the domestic heating mode. Maybe the numbers here in the upper part show the annual efficiency. So when the gas pump was operating, you served, compared to just using the conventional boiler, a little bit more than 30%, 33% when running in the heat pump mode. But since we needed at the end more energy overall, the peak load boiler was operating more than expected. So the efficiency of the heat pump boiler was for the lower than the net calorific value by 101%. So the overall savings at the end of the year, peak load and heat pump mode, was just 12%. That was lower than expected because the base load was lower than expected due to higher energy demand as a whole. So more peak load burner operation. But basically, we could prove here that if in heat pumping mode, it's easily reachable to have 30% of savings with the heat pump compared to the standard boiler. So which is almost in line with the simulation results we did above for the different climates. So the main message is economically, it might be clever to install the heat pump just for base loads to reduce the investment costs, but in heat pumping, you can save 30% of gas. So already coming to my conclusions, there are several options where gas-driven absorption heat pumps might be a very attractive solution, especially in retrofit with higher heating temperatures. It's also attractive where you might have limited electric power in certain hours of the day, but an existing gas grid, so you can do load balancing. It can be very attractive to reduce in retrofit running costs, especially in countries where you have a high difference between gas and electricity price. Just to say that in Germany, the split between gas and electricity is almost a factor of 4 between electricity price and gas price. So it's sometimes very attractive to have a high share of gas. You can do load balancing. So the operator can decide when he wants to have more on the gas grid and load instead of the electricity grid. At the moment, there are only few existing products on the market from a few companies, but more are in the research pipeline, and hopefully in 2 years from now, we have more products from well-known companies on the market. That's it, and I now come to my questions, and I'm happy to take it.
Thank you very much, Peter, for this very interesting overview of what this annex has brought for the knowledge and the potential of fuel-driven heat pumps. So I can show now the questions that we have on your topic. So there are 4 questions. Can you read them, or?
I can read and understand them. I will try to answer them, but please allow me to speak in English. Yeah. Because I have a horrible accent in French. Well, of course, the CO2 savings depends on the share of carbon in your electricity grid. So I know that you in France have a very particular situation given your high share of nuclear power, so very low carbon content. And I think then, of course, electric heat pumps are much more in favor in saving CO2. That's obvious. But for example, if you look to Germany, where we still have a lot of coal in the grid, it's different. And just to give you an order of magnitude, if you burn gas in a conventional power plant with maybe an efficiency of 60%, and then you have a COP of 0.5, you will end up roughly with the same overall primary energy conversion rate than having the gas burned in your basement with 1.5 efficiency. But as said, yes, in our case studies and in the final report, there are some numbers. It depends on your electric grid. At the end, I would say the CO2 savings are still bigger with an electric heat pumps. That's true. So from a primary energy point of view, the electric heat pump is very often the better choice, especially in France. But looking at the operational cost and the cost for savings, it might be different in different countries. I will try to read. I hope this answered the question. If not, I'm happy to go more in details. But now I'm reading the next question. Well, that's different again per country. I know that in France you have a very ambitious plan to increase the share of biogas in your grid. And I think that's a chance. In Germany, we are looking more into electrolyzers, so producing hydrogen and maybe gas from surplus renewable electricity. But I hope I get the question right. Otherwise, correct me. But I write the combination with further sources like solar thermal and waste heat are promising. I don't think that the share of renewable gas will increase very fast. So my expectation is that this technology of gas-driven heat pumps is more a bridging technology for the next couple of years to come for some countries. And at the very long run, let's say 2050, I expect that electric heat pumps are the answer. But for the bridge in between, I think it's a very promising technology. The return of invest compared to gas boilers depends really on your country. I would say difficult, because you save just 30% of gas for a higher investment costs, and it's still significantly higher compared to a cheap gas boiler. So it's a couple of years, and certainly more than 5 years for most of the countries, because the source and the technology is rather complex. But taking the CO2 savings into account, it might be attractive. It's difficult to answer, give you a hard number. There you have to go to the companies, but depending on your gas price, it's a couple of years. But compared to a gas boiler combined with solar thermal to reach the same amount of savings, you're in a fair range of return of investment. Just compared to a cheap gas condensing boiler, it's difficult. But for example, in Germany, we have some states where we have renewable heat laws. There you must bring 20% of renewable heat to a building with any new heating system installed. So you compare either to an electric heat pump or to a condensing boiler plus solar thermal, and then you are in a fair chance of having a fair return of investment, giving this regulation a chance. The level of temperature of the hot water produced, that obviously totally depends on your building. The heat pump I showed is able to produce 65 with a still acceptable efficiency for the domestic hot water production, depending, of course, on the outdoor temperatures. But it easily can produce 65 domestic hot water. Yes, there are more results available in the final report. There are a few ongoing more experiments. There are a few single-family houses because, and especially no new ones, because the most sold heat pump at the moment is the Robo heat pump with 40 kilowatts. There are smaller versions now available with 18 kilowatts, but even that's still big for new houses. So at the moment we have only 18 and 40. And so I would say it's more appealing for retrofit in large single family and maybe multifamily housings. For more conclusions, I recommend the simulation studies. The simulation studies are already published and freely available, but they will also be included in the report. In short, you have seen it in the presentation before. In retrofit, and especially multifamily, you can save up to 30% of gas. I don't recommend it for single family. And I can speak for Germany. In the cases of new single family house, it's a compression. It's a standard compression electrical heat pump is the answer. Reversible systems are available, and there are also just cooling systems with this technology. But there, I have to admit, I'm not very much in favor, because the cooling COP is in the range of 0.5, 0.7. So you burn 1 kilowatt hour of gas to generate 0.5 kilowatt hours of cold. So this is, from a primary energy point of view, not very appealing. I don't favor this kind of systems. They are done in regions for peak load where you have very high peak electricity prices. So economically, they are sometimes attractive. Primary energy-wise, it's not attractive. What are existing are some applications, for example, bakeries, where you have heat and cold demand on the same side. Then obviously it's an attractive solution, but just for cooling, I think compression is the answer. Last question. I'm not sure how to answer. Because for me, a gas heat pump technology based on aiming to electrify all applications, I have to admit I don't understand the question. I'm not aware that there's any gas-driven heat pump further there are several heat pumps on the gas-driven technology in the pipeline, but of course the trend is towards an electrification. So as said before, there is a competing situation, and there are countries with a high spread between electricity and gas price, and maybe more renewable gas in the grid, where this bridging technology of gas-driven heat pump is an interesting option for retrofit for the next 20 years to come. But on the long run, I believe in the electrification of the heating systems. Also, we had this question before, I strongly believe that we will see very large heat pump serving district heating systems. For Germany, this is definitely an option to come. When we are phasing out our coal power plants, there are gigawatts of heat missing, and I hope for heat pumps to replace this.